No need to do this now. Wait for the end of the talk, and then you can maybe kind of give me some applause. Anyway, I'm Peter Dueben. I'm working at the European Weather Center, and I'm going to talk about the progress and challenges for the use of deep learning to improve weather forecasts and also kind of climate prediction in the general picture. This is going to be much more applied in terms of like the SBC application, kind of using AI and getting into grips with it. But before I really go into the science case, I just want to give you a very brief overview about ECMWF and what we do. So we are the European Weather Center, or this kind of strange acronym of ECMWF, which means that we do medium-range weather forecasts, which then means that we kind of go something like a couple of days into the future and we kind of do the predictions globally. So we kind of really focus on global weather predictions a couple of days into the future. And we are research institutes, but we also have this kind of 24/7 operational weather service. We are an independent intergovernmental organization supported by 34 member states that are kind of depicted here. We are in Reading, so not too far away from London. We have 350 members of staff and something like 100 researchers. We also have 2 supercomputers. We have kind of 2 4 petaflop machines that basically we use to do our research, but also to do our operational forecast. And we are the home of the so-called integrated forecast system, which is one of the best global weather forecast models of the world. So we kind of develop our own model and our own data simulation infrastructure, which involves quite a lot of coding and high-performance computing. Predicting weather and climate, I don't know. I mean, I said that I'm kind of looking into the medium-range weather forecast a couple of days into the future. So I'm not going to ask you how many of you will actually believe in a 5-day weather forecast. So it's quite a difficult thing to do, right? It's not totally easy. And why is it so difficult? This is a picture that was taken from the Apollo 17 mission, and it kind of shows nicely what the challenges really are here. So one of the things is that the Earth is quite complex, right? You have different components. You have sea ice and land ice. You have the ocean. You have the atmosphere. You have land and topography interacting with each other. And this basically means that our models have something like 1 million lines of code to kind of represent all of these different components that are interacting with each other. The other thing is that we have kind of a lot of features like the clouds here. And you can also kind of see scale interactions, like really kind of turbulent flow fields in the atmosphere, which is another thing that's really a problem. You have a chaotic field, and it's kind of really difficult to kind of predict something long into the future if your perturbations grow exponentially. And another thing is also that the Earth is quite big, right? So even kind of on the fastest supercomputer that we have at the moment, we're running with something like 10-kilometer grid spacing in the weather forecast at 100-kilometer or 50-kilometer grid spacing in climate prediction. And that basically means that kind of things like important things like clouds are not really present at the scale, right? I mean, typical clouds are much smaller than 10 kilometers, which basically means that a lot of the important processes that we need in Earth system science and weather and climate predictions are actually not resolved on our grid that we have, and we need to so-called parameterize them. So we basically need to add terms to the equations to represent those processes that we can't resolve explicitly. So the Earth is complex, it's huge and chaotic, and we do not have sufficient resolution to resolve all the important processes. So where does machine learning and AI comes into the game now? Basically, we have this kind of very complex setup. We have a lot of observations as well, so we have a lot of data present. We have all these different complex components interacting with each other, and we can argue that there are a lot of applications actually for machine learning in this kind of environment. So we have a lot of different complex systems that we cannot really understand and need to learn, and we can use machine learning to kind of do some steps in here. So basically, the Earth system has many components that show nonlinear dynamics. We have plenty of observations and often need to apply rough approximation to formulate our models. So that's a good environment for machine learning in principle. What is machine learning? All of you know, I would believe, but I still have kind of, I couldn't resist to put a sketch of a neural network here. So you basically have a system that is learning from data. So you have input and output pairs of a complex nonlinear system, and you're just learning how to represent the system kind of with a tool. And then you basically end up with a computer model that you can use as a black box to kind of represent the system in whatever way you want to. And that's kind of really good, a very promising tool if you have this environment of kind of a lot of uncertainty, but a lot of data and a lot of kind of individual components that you want to represent. So that's good. And indeed, if you think about the workflow that we have in numerical weather predictions, kind of starting from observations that have some error, kind of they're going to be pre-selected, kind of put via data simulation into a forecast model that's going to run forward. Then we have product generation, and then we kind of distribute the data all over Europe to member states, but also users all over the world. And if you think kind of where machine learning is coming into, you have kind of a couple of boxes here that show you that really all over this workflow there are potential application errors for machine learning in this field. And it's kind of now up to the community to really understand where are these applications kind of really useful and where are they maybe not as good as state-of-the-art methods in principle. So what I'm going to do in the next couple of slides is basically I'm going to run you through a couple of examples that I'm working on with machine learning and weather forecasting, and then I'm kind of also going to discuss the challenges, because people are not talking often enough about the challenges that we face with kind of machine learning in these complex systems. So the first thing is that we kind of may just want to learn the equations of motion. So basically, neural networks are able to learn complex nonlinear dynamics as a black box, and this complexity kind of has really shown to be extremely, well, surprisingly kind of big for what machine learning tools are able to do. So why not just kind of take our observations, for example, satellite observations, and just learn the equations of motion for the weather forecast in principle. So we could base in principle our entire weather forecast on a neural network. And this basically means that we could get rid of Navier-Stokes equations that we typically use to kind of solve atmospheric dynamics, and just say like, okay, well, we know the equations, but we can't solve them anyway. It's kind of just, there's no analytic solution, and the supercomputer is kind of not a very good tool in principle, because we have discretized and we have subgrid scale variability that's kind of really kind of perturbing our forecasts. And as I said before, we have really a lot of data. So we have 210 petabytes of primary data at ECMWF that have somehow to do with weather and climate. So let's just learn the equations that we do. And we've kind of done this in a very idealized setup. So I've retrieved data sets from a so-called climate reanalysis set, where basically you have the best state of the atmosphere as we know it for a couple of decades. And I've retrieved 65,000 global data sets for one specific field, which is called geopotential height at 500 hectopascal. So it's just a 2-day field all over the globe. I've mapped the field onto a longitude-latitude grid, like with 60 times 30 grid points, so really very coarse resolution. And now I'm used the neural network to actually learn the right-hand side of the equations of motion. What does it mean? If I have hourly data, I can basically just train a neural network to kind of make the update from 1 hour to the next hour, and kind of do this for a couple of decades of training data. And in the end, I end up with something which is really kind of able to solve my differential equation, if you want so. And kind of to go more into the details, I basically used the neural network streaming through this kind of 2-dimensional grid, having a bit of a stencil, very similar to finite different methods that you typically use in computational fluid dynamics. Did it work? Yes, it did. So I could actually kind of, now that I've learned the right-hand side of the equations, I could actually make predictions into the future. So I could literally do a neural network forecast of the weather as we see it in the couple of days future. So that's kind of a forecast error of this one field, the geopotential height, for 5 days into the future. And what you see is a black line is a neural network forecast error that you have, and it starts low and grows as normal. And you also have the coarse resolution IFS. So this is really a coarse resolution IFS. So the operational forecast would be somewhere here. So it's kind of definitely nowhere near the complexity of what we need. But in principle, you compare like with like in the slide in terms of the complexity of the model system that we have. And as you see, the neural network is not performing too bad. So as first shot, tackling against something that is kind of in place for 30 years, it's not bad at all. And also, if you look into the dynamics, it's kind of, again, like one of those surprising applications where kind of things really look quite well. So this is a 24 hours analysis of this kind of field that I'm looking into the forecast. And this is a neural network outcome, and you see that the features are very similar. And even if I just think about the update of the field for 24 hours, you can see from the analysis, like the reference, truth, and the neural network, you see the features that you want to see in terms of mid-latitude jets propagating and all these kind of things. And as a matter of fact, if I would show you videos between the analysis, the truth, and the neural network forecast, you wouldn't see a big difference. So the dynamics is actually also working surprisingly well. However, here comes the challenges now. There's no kind of immediate way that we would know how to kind of increase complexity of the system further. So kind of making just giving it all the fields that we have doesn't work. So we need to kind of think about ways how to kind of increase complexity in the setup. And also, the model runs crash after a couple of weeks. So if I kind of have a neural network model and run it forward, it's going to crash. And there's This doesn't really come as a surprise because we don't really told them anything about conservation of energy or these kind of interesting features that we want to kind of conserve if you make a weather prediction. So there's a lot to learn kind of from this setup, and kind of a lot of to find that there are still a lot of challenges around if you kind of want to apply these black boxes to physical systems. I'll come back to this later, but now I'll basically go on to something which is more HPC. And it's basically the idea to use a neural network to emulate existing parameterization schemes. So a parameterization scheme is something for a scheme that is representing one of the components of the system, for example, a cloud, that we typically can't really represent explicitly. So it comes with a lot of uncertainty in principle, and a lot of parameter tuning if you want. So what we do now is that we kind of run our model forward, and then we store input and output pairs of this parameterization scheme. And we store as many as we want. We can generate, give me a disk and I can fill it. It's no big problem to generate data here. And then we use this data to train a neural network to do exactly the same thing that the parameterization scheme did in the first place. And by doing this, I kind of generate a neural network that I can then use to replace the existing scheme within the forecast system. Why would you do this? A large fraction of the computational cost is actually generated by the part of the parameterization scheme. It's something like 50%, or maybe a bit less, but this kind of order of magnitude. The parameterization schemes are really ugly. So we're talking about Fortran code. 90% of the model code is parameterization schemes, and it's written by domain scientists. And it's really hard to kind of make it running efficiently on HPC systems. So the optimization of this code is very difficult, and we're kind of struggling to get something like 5% peak performance. However, if you kind of think about the neural network and have the same level of complexity in principle, they are highly optimized, and we can just use kind of standard libraries for machine learning and port them to GPUs or even KNL or whatever you have. And so base portability comes for free, and we'll also be talking about dense linear algebra now, so we kind of really speed things up in terms of the performance of the system. So we hope that the deep neural networks will be almost as good as the original schemes, but much more efficient. And we did now a couple of tests. One of them is kind of running with our radiation scheme. So the radiation scheme is basically the representation of like radiation coming from the sun interacting with clouds and the surface and going back to space. And what the radiation scheme is actually doing is calculating the heating rate at the different vertical levels. So it's kind of quite an expensive part of the parameterization schemes. And we have a collaboration with NVIDIA where we kind of ported our radiation scheme onto neural networks, and we get quite good results. So this is kind of just one of the fields, the downward solar radiation at the surface, and one of them is the neural network scheme, and the other one is the original parameterization scheme. And we can see that the system is working quite well. We now have also free-running simulations that are stable, and we get something like a speed-up factor of the order of 10, but we still need kind of to look into more into detail. And it's kind of still not there yet, and we can still not say that we're neutral, so we still get degradation of results using this neural network emulation, but there's a lot of scope here to kind of increase performance of our models. Another work that we've done together with a group in Oxford, Matthew Chantry and Tim Palmer, where we looked into the gravity wave drag, just another scheme that's kind of representing the interaction from topography and like wind going over topography, generating waves that are propagating up in the atmosphere and breaking at one point. And you see the original scheme on the left and the neural network on the right, and the difference. And basically, given the amount of uncertainty that these kind of schemes really have in our system, this is probably good enough. And we can, well, let's see where we get there. But there's some hope that this emulation of parameterization scheme is really kind of going to be very beneficial for us. This is probably, I'm not sure whether this really makes sense to show the slides, because you will know anyway. But basically, I just wanted to phrase once more that weather and climate simulation are definitely high-performance computing applications. So you see here on the slide, you see the performance that we had at ECMWF over the years increasing. That's a peak performance. And the resolution that we had at the specific performance levels that we had. And then you can see the different properties that we could then resolve in our model system, and kind of that helped us to improve our predictions. And one thing that is kind of almost depressing is, as you all know, is basically if you look at the sustained performance, we're starting from something like a factor of 2, and now we're going all the way down to something like 3% of peak performance that we kind of can actually make with our models. So the question is, machine learning kind of now has a very strong impact on hardware development in principle, and I guess this ratio is probably going to be even worse in the future if we kind of don't follow this trend. And kind of learn how to make use of machine learning hardware in principle for our system. So actually the question is, can we use deep learning hardware for conventional models in this case? And we've tried to kind of port one of the most expensive kernels of our models to kind of work on machine learning hardware and machine learning accelerators. So this is basically the fraction of the cost if you have a very, very, very high resolution simulation of and you can see that more than 50% of the cost is kind of spent in what we call the transforms. And the transforms is in our model, which is a spectral model, basically a bunch of fast Fourier transformations, but even worse, Legendre transformation. And they kind of really building the majority of this cost, building this kind of 50% cost block in our model simulation. So the Legendre transformation is the most expensive kernel for high resolutions in our system, and it's basically nothing else than standard matrix multiplication, but many of them. And now we kind of investigated whether we could use, in principle, half position also to do the same job, and it turns out the Legendre transformation is linear, so we have to rescale it to kind of fit into the exponent range of the half position. But if we do this, we can actually kind of calculate the Legendre transformation in half position. And this means that we could use things like Volta GPUs and the tensor cores on them, like AI accelerators basically, and do half precision matrix multiplication, which is kind of the prime application for machine learning hardware. And this would, in principle, in terms of peak performance, bring us up by a factor of 16 in comparison to double position floats. So that's obviously not the factor that we kind of may be able to get in the end, but it's still an interesting factor to look into if you want to kind of get the cost down for this very expensive kernel. And it turns out that kind of results look really promising. So these are error plots for geopotential height gains for 3 different areas on the globe. And you see the double position reference, the half precision transforms, and the emulated tensor core. So I should say that we haven't really ported the Legendre transformation to tensor cores yet. We really have just used emulators to emulate the reduction in precision. However, in principle, we are more or less neutral for these kind of very limited statistics of runs. So it's kind of really promising, and we need to kind of look more into this, I believe, in the future. However, more needs to be done to actually kind of verify that we're neutral. So it's still early stage. Okay, now I have shown you what amazing things you can do with machine learning and how this is going to impact on us. And I'm now going to talk more about the challenges that we're kind of going to face as a community, and in particular those of the community who are looking into machine learning. To some extent, we have now shown a period of like something like 2 years where people have shown a lot of nice pictures and videos, and basically have published a lot of interesting papers showing where we can use machine learning principle. But now it's kind of up to us really to prove that these tools are really better than state of the art within the next couple of years. And this sounds easy with these kind of amazing tools, but it's actually quite difficult. And in particular, it's difficult to build useful tools, meaning that you can actually show in 2 years from now that those tools have been able to really improve weather predictions for increasing performance and all these kind of questions, also to improve our understanding of the Earth system. And I believe that's a very challenging challenge in principle. Why is it so? Because our models are already really, really good and really, really sophisticated. So this is kind of the cloud top temperature that we get from a satellite and from our simulation running at the highest resolution possible. And I'm not going to tell you which one is which, but you basically can see this amazing level of details, for example, on cloud cover over Indonesia. So we're already running at something like more than 1 billion degrees of freedom in these kind of weather forecast models, and it's not easy to touch such a system and kind of make any change to it, really. So global simulations show a breathtaking level of complexity and can present many details of the Earth system in principle, and it's difficult for machine learning to really kind of push something there. And there are also very challenging scientific questions that we need to tackle. There's no problem in principle to apply a black box to a physical system. I'm not saying this, but you have to be careful. And one of the things that's really difficult is how to project our knowledge that we have about the Earth system into this black box framework. And I think we need to kind of learn more how to do this and how to kind of project, for example, the knowledge we have over Navier-Stokes into kind of an architecture, network architecture blueprints that we could use for these systems. It's also, on the other hand, very difficult to diagnose physical knowledge from the network once you have trained it, and you need this basically to understand, for example, how processes interact within the Earth system, because if you find out that convection in the tropics is not triggering gravity waves or something like this, as it should do, and in a physical system you can basically kind of look into it and fix it, but in a network system it's very difficult to understand what's going wrong. We need to understand how to remove biases from neural networks and how to secure conservation laws. We need to understand how to pick hyperparameters for training, because at the moment it's just painful work, but I'm very, I I think it's promising to just kind of learn from experience here. We need to learn how to guarantee reproducibility. For example, if you kind of emulate a parametrization scheme and we have an upgrade, we need to make sure that we will at all costs be able to kind of get good results again. We need to get beyond dense networks and still take properties of something like local properties into account, basically saying we need to kind of build machine learning tools that are scalable. We need to fix interactions between model components. We need to learn how to interface neural networks with legacy code, which is surprisingly difficult. I never thought it would be such a pain, but it wasn't only me who kind of really stumbled over this in the last year. We need to learn how to design good training data, explore the full phase space, in particular in terms of climate change. You've seen the temperature warning over here, so climate change in action. And you need to be able to generate labeled data sets on a large scale for training. So how can we do this? How can we kind of couple these weather and climate models in the middle to something like deep learning architecture on the outskirts? I will really believe we need to do more of this kind of really research work in terms of how do we actually emulate very simple differential equations. So kind of really learn how from very simple physical principles how to kind of, for example, make sure that you secure something like conservation laws. So that's a very good university type research study, but then also in terms of HPC and something like a center for ECMWF, we need to learn how to scale these kind of networks to something which is really high performance computing applications, because there are not many of those around yet. So we need to learn something to build a network, a blueprint for a network that is able to kind of get something like 1 million inputs on the three-dimensional sphere, on the of a three-dimensional field on the sphere, and kind of still make very efficient training there. We need to study the representation of variability and correction of systematic errors for neural networks. So it's kind of more the error detection and uncertainty quantification in models. We need to build community tools in the form of benchmark problems. Sorry, I can't really read it. So as a community, we kind of need to come up with some sort of benchmark tools. And then also we need to focus really on the useful tools. So really to be able in 2 years from now to show that we have done something new that wasn't possible before. And I think that's hard work, and it also will require a lot of customized machine learning architecture for weather and climate application. So just to give you one example, if you take the nonlinear Burgers equation, just the plain one-dimensional differential equations, and you have a term p that you don't really know, which is kind of the situation that we have in our field. The conventional approach would be to discretize those differential quotients, these terms here by differential quotients, and put them on a grid and kind of build a parametrization scheme that tries to represent this p term with a stochastic forcing. The data science approach, and this was kind of what I've done with the geopotential height study at the very beginning, would just be to kind of take input-output pairs on a grid and kind of do the update with a neural network. And I believe we would really need to kind of combine the two approaches if we really want to be successful with machine learning in weather and climate. So we would need to learn how to kind of build neural network structures from the differential equations, and then kind of build this all into a kind of scalable HPC framework and learn the weights in the typical way we do from neural networks to really kind of do the best of both worlds. Okay, these are the conclusions, but I'm not going to read them out, and I thank you for your attention.